Hello everyone, nice to talk with you again. This is Ronaldo. In the previous chapter, we've talked about what is working directory, what is repository, and the basic object types in it. Now we are going to further talk about how Git works with these concepts. Actually, we have experienced the basic workflow before. Now let's again review the process. First, let's see the workflow of how you use Git to submit a commit. Here's a rough step of how to create history. We need to keep in mind that all the works we do, such as changing files in working directory, adding them to repository, making a commit, they will happen in our local machine. You don't need network since you are not directly working on the remote side. The principle is that we clone or pull changes from the server and work in local. After all your work is done, push your changes into the server. We call the repository in server as the remote repository. In general, you will experience the following steps. First, make any changes in your working directory. Second, using git add command to add the changes into the local repository. Third, using commit command to create a version and save the commit object into your local repository. Fourth, you can repeat the steps in your local repository. Remember, all the changes you made happen in your local repository. The changes are not yet pushed into the remote repository. Fifth, until you think you're ready to push your changes into the remote repository, using git push to push all the changes into the remote server. That's the real submit. And this time, people can get your change from the remote repository. Above is the rough steps. Remember, commands only like fetch, pull, and push are interacting with the remote server. To better illustrate the workflow, let's take a further look. Here you may meet some branches. Don't worry, we will explain it later as a core concept. Currently, just follow me and try to understand the example. Usually, we have a remote repository. We call it origin. We can get access to the repository by its URL. Either HTTPS protocol or SSH protocol works. For example, we have a remote repository at the following URL. This is where we clone source code and where to push our changes. At the very beginning, you need to use git clone command to clone the repository onto your local disk. And then you got the repository. You then work as if you were communicating with the remote repository directly, which actually is not the case. As we've mentioned before, all the changes you do are in your local machine. Unless you push your changes into the remote repository, no one will get your local changes, although you have a variable history versions on your local. Keep in mind, these changes are in your local. You need to push them into the remote repository if you would really like to share your changes. As soon as you clone the repository, you get everything the remote repository owns. Here, let's assume that we have two commits in the remote repository. The two commits are managed by a dev branch. After you clone the repository, you also get two commits and an origin dev branch, which is to sync the remote repository dev branch. We will explain in more details about the origin dev branch, so don't worry about that. Your working branch is named as dev, the red rectangle I draw in the graph. This is a local branch. By default, it points to the last commit in the default branch in remote repository. Here you just need to know the origin dev branch and the dev branch are not a same branch, although they point to the same commit at the very beginning. It is designed on purpose that you will feel like you are working directly on the remote repository. Now make some changes. Remember, all the changes happen locally. So I use a different color to describe those changes. For example, you make two changes and add them, commit them into the repository. See, although you get the two new commits, the remote does not change. If you would like to push a change to remote repository, you need to call git push command to push them. Here you see all your changes finally go into the remote repository, and now people can see your changes are remote. Your origin dev then pointed to the same commit as your local dev branch does. So does the dev branch in remote repository. It's a very simple and clear slide to illustrate what happened to the local repository and remote repository when we call some basic commands. You form a history locally and then push them into the remote repository. Now let's talk about the status of each step. First, you don't do anything and run git status to see the status of your working directory. The command line will tell you nothing to commit, working directory clean. Then you make some changes under your working directory. Run git status. You will get some messages from the command. The red line is telling you what have been changed. Now you should add your change into the index and cache it into your repository. As we've mentioned before, using git add to execute the request. Here you will get some message from the command. The green line is telling you what have been added into the index and cached into the repository. Index is a middleman. When your changes have been added into index, they are not yet committed. And that is to say, you still can add other changes into the index and then finally commit. The index is between the working directory and the repository to stage or collect alterations. When you manage your code with Git, you edit in your working directory, accumulate changes in your index, and commit whatever has masked in the index as a single change set. If you feel confusing, don't worry, we will explain it later in more details. It's time for you to commit now. After you commit, this version will exist in your local repository as a commit, since you have a new commit object saved in the repository, and its parent is the last commit before you execute the commit command. Running stages, you will get such a message from the command line. It tells you that your working directory is clean again. All the commands we have run above actually happened in local, so your change does not exist in the remote repository. Until you successfully run git push command, your changes then submitted into the remote repository. Now let's go into more details about the stages. We would like to see what happened when we change, add and commit history. Why the command line returns us different stages. There are three areas that affect the stages: their working directory, stage, and the repository. We've already known well of the working directory and the repository. The stage is what we mentioned before is a middleman. We don't directly commit the change into the repository. Instead, we maintain a stage phase for us to ensure whether we submit these changes into the repository. Stage is like a cache. We also use a tree to describe the stage. Let's now take insight to see the relationship between the three parts in different situations. Clean stages. In these stages, the file contents and the structure are the same among working directory, stage, and repository. If we use tree to describe, the plots of the root tree should be the same. Let's check the table, which describes the file stages in three areas: working directory, stage, and repository commits. In file A, the content is full. SHA is 191028. In file B, the content is bar. SHA is 5716CA. Running the git stages, it will tell you nothing to commit, working tree clean. Now we make some changes. We convert the file B, changing the content to QUUX. I use orange to show the change. We can see that the SHA for file B changed to 3996DD. As we have not yet used the git add command to add the change into stage, the files in stage area and in repository remains the same as before. We call these stages as unstaged stages. Keep in mind that in this phase, there's no blob for the new file B in the repository. Why? I think this should be an easy question for you, because you have not yet run git add command to add them. Let's check the table, which describes the file stages in three areas. We can see that both file B in stage and the repository commit points to the old file B, whose SHA is 5716CA. But the file B in working directory has been changed and its SHA is now 399DD. This status is the so-called unstaged status. You can run git status to check it, and it will tell you change not staged for commit, modified file B in red text, and will imply you to use git add to update what will be committed, or use git checkout to discard changes in working directory. Now I think you should fully understand why it gives you such suggestions. Only if you use git add command could you add the change into the stage and keep it in the repository, and then step into the next stage. Or you use git checkout to discard the change and back to clear stages. Now let's go into the next step. We use git add command to add all the changes into stage. See, we have the new file B in the repository now, and we found that the file B in index points to the new file B, 3996DD. Both file B in working directory and stage point to the same file, and the file B in commit 1 in repository still points to the old version, 5716CA. Again, let's check the table, which describes the stages in the three areas. Yes, it shows that the file B in working directory and stage are the same. They are the changed file. The file B in repository commit remains the old version. We call these stages as staged. Running git stages, it will tell you change to be committed, modify the files. I believe it's very easy for you now to know what exactly the command is telling you. You are now at staged stages, but you have not committed your change yet. The change now is managed by the middleman, the index. You still have chance to change it and add the change again into the index and prepare for your next commit. If you use git reset command, you can go back to the last stages to unstage your change. If you run git commit command, you can go to the next stages as committed. Now let's run git commit. See that there's no change in the working directory and stage, but in the repository, we have a new commit that contains a new tree, pointing to the file A and the file B, 3996DD. Let's check the table, which describes the file stages in the three areas. Now the three areas keep the same stages. they point to the same files. Please make sure you understand the stages since it's a very important concept in Git workflow. If you don't fully understand the stages, it's better to watch the video again, and if possible, I encourage you to do some exercises yourself and running the commands to check your knowledge. So here is the conclusion. We use git add command to update the stages from unstaged to staged. We use git commit command to update the stages from staged to committed. And we use git push command to push the commit into the remote server. With the above knowledge, we are now able to talk about the reset command. In Git, the reset command is confusing for a beginner, since the different argument will reset you to a different stages. Please use git reset help to carefully read the details about the command. Here, we mainly talk about 3 arguments. As we all know now, between 2 commits, actually there are 2 other stages. That is the unstaged stages and the staged stages. The unstaged stages will keep the changed file in your working directory, while the staged stages will keep the changed file in cache. Neither the 2 stages change the files in commits. So when we're using git reset command, we can actually reset it to the following stages. 1. Using git reset --hard to go to the last commits. In these stages, as we've talked before, the files in the working directory and target commit keep the same. If you run a git stagers command, it will tell you nothing to commit. So if you want to totally reset to the target commit, or to say you just want to go to a certain version, use the --hard argument. 2. Using git reset --mixed, or simply using git reset because the default argument is --mixed to go to the unstaged stages. In these stages, your working directory owns the next version's file, while your local commit still points to the target commit. If you run a git stages command, it will tell you that some files changed. You can use git add to add the changes to the stage, or you can do some changes here and then add them into the stage again. 3. Using git reset --soft to go to the stages between the 2 commits. You will find that you have already staged the changed files, but your last commit points to the target commit since you have not committed it yet. I decided not to make any example here since I encourage you to do some exercises yourself. Now you should be able to make some example yourself and play with it. Next, we will go to the very core concept of Git, the branch. Nearly every VCS has some forms of branching support. Branching means you diverge from the main line of development and continue to do work without messing with that main line. In many VCS tools, this is a somewhat expensive process, often requiring you to create a new copy of your source code directory, which can take a long time for large projects. Some people refer to Git's branching model as its killer feature, and it certainly sets Git apart in the VCS community. Why is it so special? The way Git branches is incredibly lightweight, making branching operations nearly instantaneous and switching back and forth between branches generally just as fast. Unlike many other VCSs, Git encourages workflows that branch and merge often, even multiple times in a day. Understanding and mastering this feature gives you a powerful and unique tool and can entirely change the way that you develop. You will totally understand why after we go inside the branch concept. Please look at the slide. I made a picture to illustrate the concept of branching logically. In the repository, we have several commits consist of the history. Besides, we have a master branch and something called head. So, what is a branch in Git? A branch in Git is simply a lightweight movable pointer to one of these commits. The default branch name in Git is master. As you start making commits, you are given a master branch that points to the last commit you made. Every time you commit, it moves forward automatically. The master branch in Git is not a special branch. It is exactly like any other branch. The only reason nearly every repository has one is that git initiate command creates it by default, and most people don't bother to change it. So keep in mind, the branch is nothing but a pointer points to one commit. Like the master branch I draw in the slide, it points to the commit C3. Then what does the head means in the slide? Don't worry, let's move on to create a new branch first. Using git branch dev to create a new branch named dev. See, there's now a new branch points to the same commit as master does. When you're using git branch command, it creates a new pointer to the same commit you are currently on. Now we have two branches. Then how does Git know what branch you are currently on? It keeps a special pointer called head. Note that this is a lot different than the concept of head in other VCSs you may be used to, such as Subversion or CVS. In Git, this is a pointer to the local branch you are currently on. In this case, you are still on master. The git branch command only created a new branch. It did not switch to that branch. If you would like to switch to a branch, using git checkout command to switch to the target branch. Now we are going to the dev branch. Actually, when you use this command, git simply moves the head to point to the dev branch. Git branch plus git checkout equals git checkout -b. Let's continue. We assume our head points to the dev branch. We now make some changes and commit. It is interesting because now your dev branch has moved forward, but your master branch still points to the commit you were on when you run git checkout to switch branches. What if we now switch back to master branch? Run git checkout master to switch back to the master branch. We see that the head now moves to the master branch. And if you check the working directory, you will find that the files in working directory were when we left the master branch. That command did two things. It moved the head pointer back to point to the master branch, and it reverted the files in your working directory back to the snapshot that master points to. This also means the changes you make from this point forward will diverge from an older version of the project. It essentially rewinds the work you've done in your dev branch so you can go in a different direction. It's important to note that when you switch branches in Git, files in your working directory will change. If you switch to an older branch, your working directory will be reverted to look like it did the last time you committed on that branch. If Git cannot do it cleanly, it will not let you switch at all. We have already known the branches in Git. Now we will talk about another important concept based on branch, that is merge. There are mainly two kinds of merge in Git. One is called fast forward and the other is a non-fast forward, or we call it basic merging. Let's reuse the example. Assume we have made a fix called C4 on dev branch. Now we are going to switch back to master and merge the fix into master. First, we need to check out to master branch. Then we run git merge dev to merge the changes in dev branch to master. You will notice the phrase fast forward in that merge. Because the commit pointed to by the branch you merged in was directly upstream of the commit you are on. Git simply moves the pointer forward. To phrase that another way, when you try to merge one commit with a commit that can be reached by following the first commit's history, Git simplifies things by moving the pointer forward because there is no diverge work to merge together. This is called a fast forward. After doing the fast forward merge, you simply find that the only change is the head moved master branch forward, and now master points to C4. Your change is now in the snapshot of the commit pointed to by the master branch. Check your working directory. You will find that you already have the fix in C4. If you don't need the dev branch now, simply use git branch -d dev to delete the merged branch. Now, let's turn to the basic merge. Suppose we create a dev branch when the master branch points to the C2. Continue work on master and commit C3. Then you switch to dev branch and commit C4 and C5 to fix an issue. Finally, you would like to merge dev branch into master. All you have to do this moment is to check out the branch you want and run the git merge command. This looks a bit different than the fast forward merge we did earlier. In this case, our development history has diverged from some older point C2. Because the commit on the branch you are on, C3, isn't a directory ancestor of the branch dev we are merging in, Git has to do some work. In this case, Git does a simple three-way merge using the two snapshots pointed to by the branch tips, C3 on master and C5 on dev, and the common ancestor C2 of the two. Instead of just moving the branch pointer forward, Git creates a new snapshot that results from this three-way merge and automatically creates a new commit, C6, that points to it. This is referred to as a merged commit, and is spatial in that it has more than one parent, C3 and C5. Let's go detail into the three-way merge algorithm we mentioned before. Let's reuse the same case as the basic merge we talked before. C3 is the branch tip in master branch. In this case, it is the local target commit, or to say, it is the commit that could reflect the current working branch. C5 is the branch tip in dev branch. In this case, it is the remote target commit, or to say, it is the commit we would like to merge into master branch. As we all know, we can simply tell whether two files are the same by their SHA code described in the tree object. The three-way merge algorithm is very simple. Compare a snapshot of files in local branch C3 with common ancestor C2, and then compare a snapshot of files in remote branch C5 with common ancestor C2. We may meet the following situation. The first situation: a same file changed in both branch, then it needs to be merged. If the same file has been changed the same part in both branch, then it needs to be resolved. Otherwise, it can be simply merged. In the end, a new file will be created as a snapshot and finally keep it in the new merge commit as the file blob. The second situation, neither the same file in two branches is changed. Then take the file in ancestor commit as the file in the merged commit. The third situation, one of the branch changed. Then take the changed one in the merged commit. In our case, we assume that we have 1.txt and 2.txt in C2. By comparing with the ancestor commit C2, we can find that in C5, both 1.txt and 2.txt changed. In C3, 1.txt changed, but 2.txt didn't change. 1.txt in C5 and 1.txt in C3 are different because they have different SHA-1 code. Obviously, this is the first situation we mentioned before. 1.txt need to be merged. If the change was not in the same part of the file, then Git will auto-merge the file. Otherwise, you will meet a confliction. In that situation, you will have to resolve it before you commit the merged commit. Git hasn't automatically created a new merge commit when you meet a confliction. It has paused the process while you resolved the conflict. If you want to see which files are unmerged at any point after a merge conflict, you can run git status. If you want to use a graphical tool to resolve these issues, you can run git merge tool, which files up an appropriate visual merge tool and walks you through the conflicts. It is highly recommended that you use a merge tool. I would like to show you the merge tool I configured in .git-config file later. After you exit the merge tool, Git asks you if the merge was successful. If you tell the script that it was, it stages the file to mark it as resolved for you. You can run git status again to verify that all conflicts have been resolved. Continue. 2.txt is the third situation we mentioned. Since 2.txt in C3 didn't change, then simply take the file in C5 as the one in the merged commit, C6. Let's check the final result in the merged commit C6. We found that 1.txt is a new file that is different among the one in C2, C3, and C5. This is because in C6, the 1.txt is a new file that merged from the three-way algorithm. 2.txt is the same as in C5. Now I would like to show you the merge tool configuration. Note the arguments of the merge tool. Pay attention to the color. I stress the arguments by the colors we draw in our case. I guess now you should fully understand the meaning of the arguments. This is a simple but very important algorithm in Git. Please make sure you understand it. If not, please watch it again, or you can open the PPT I sent to you to replay the animation. A better way is to design some cases yourself with Git and see if everything goes in accordance with your thought. Now let's talk about the rebase. In Git, there are two main ways to integrate changes from one branch into another, the merge and the rebase. So what's the difference between merge and rebase? Let's first see what will happen if we use rebase instead of merge in the last case. The same target, we would like to merge the dev branch into master branch. But now you have a different choice. You can take the patch of the change that was introduced in C4 and C5 and reapply it on top of C3. In Git, this is called rebasing. With the rebase command, you can take all the changes that were committed on one branch and replay them on another one. Yes, very clear. Seems as if the two branches had never diverged. At this point, you can go back to the master branch and do a fast forward merge. There's no difference in the end product of the integration, but rebasing makes for a cleaner history. If you examine the log of a rebased branch, it looks like a linear history. It appears that all the work happened in series, even when it originally happened in parallel. Rebasing replaces changes from one line of work onto another in the order they were introduced, whereas merging takes the endpoints and merges them together. Then, let's take a further look to see how rebase realizes that. Actually, it works by going to the common ancestor of the two branches, the one you are on and the one you are rebasing onto, getting the diff introduced by each committer of the branch you were on, saving those diffs to temporary files, resetting the current branch to the same committee as the branch you are rebasing onto, and finally applying each change in turn. Let's watch the animation to show the process. Here will happen a recursive three-way merging algorithm. Note that the purple one is base ancestor committing in each three-way patch. The first time, C2 as ancestor, C4 as remote, C3 as local, and we got a new commit, applied C4. The second time, pay attention that the best or nearest common ancestor with the two branches now C4. Apply the C4 as local, C5 as remote, and we got a new commit, applied C5. This is how the new history was formed. This is the concept of rebasing. Is it interesting? Don't hesitate to have a try on yourself. Another confusing concept is pooling and fetching. Now let's talk about them. With all the knowledge we now possess, we are able to talk about some concepts on the remote side. Remember that we always mentioned an origin in our repository? What actually is the origin? Actually, origin is not special. Just like the branch name master does not have any special meaning in Git, neither does origin. Where master is the default name for a starting branch when you run git initiate, which is the only reason it's widely used. Origin is the default name for remote when you run git clone. Then it's easy to understand that there's a branch called origin-master which keep track of the master branch on the remote server. You won't move this branch until you use git fetch or git pull to sync the status of the branches on the remote server. What is fetch and pull then? What is the difference between them? I would like to show you the concept in the next slide. Now we can understand like this. While the git fetch command will fetch down all the changes on the server that you don't have yet, it will not modify your working directory at all. It will simply get the data for you and let you merge it yourself. However, there is a command called git pull, which is essentially a git fetch immediately followed by a git merge in most cases. Git pull will look up what server and branch your current branch is tracking, fetch from that server, and then try to merge in that remote branch. Generally, it's better to simply use the fetch and merge commands explicitly, as the magic of git pull can often be confusing. Now let's go to the next slide to have a better understanding. Let's assume that we have just cloned a repository from the remote. In this case, the default server name is called origin. So when we say origin, it actually refers to the remote server repository. Let's take the dev branch as example. We have 3 commits at the very beginning. I believe now you can draw the picture in your mind that we have a dev branch points to C3, like the server. But have you ever thought about where does this local dev branch come from? You may take it as the copy of the pointer from the remote origin server. Actually, this is not quite correct. In fact, there's a copied branch called origin-dev in your local repository. And this pointer is the exactly pointer that is used to keep sync with the remote origin dev branch. Here, we use purple to draw the branch. Your local branch was copied from this purple origin-dev branch and set to be your working branch. So when you commit any changes, you don't change the origin-dev branch. Instead, you're affecting this local dev branch. Let's continue. Here, we suppose we make some changes in local repository and submit two commits A, B. See, the local dev branch moves to B, but the origin-dev branch in your local repository keeps the origin status. It still points to the commit 3. Now, let's suppose someone has pushed his commits 4, 5 to the server. We can see that the dev branch in remote now moves to the commit 5. As you haven't communicated with the remote server yet, the origin-dev branch hasn't changed. You probably would like to sync with the remote repository. You can use git fetch to fetch down all the changes on the server that you don't have yet. Now you could see that the origin-dev branch in your local repository changed. It points to the commit 5 that was just synced by the fetch command from the remote server. A very important thing is that your dev branch and your origin-dev branch diverge now. If you check your working directory, you will find that nothing changed. Why? I hope you can now figure it out yourself, and you should able to find that your working branch is the snapshot of the commit your current working branch points to. As I've mentioned before, your dev branch and origin-dev branch are not actually the same branch. Although your origin-dev branch has been updated just now, your working branch won't change. It is still the snapshot of commit B. If you would like to get the latest contents from the server dev branch and reflect it on your working directory, guess what you should do? Yes, simply use git merge origin-dev. This works very well. You will get a merged commit which contains the changes in commit 5 and the changes in commit B. Another way to get the latest change in commit 5 is to use git rebase command. Using git rebase origin-dev and see what will happen. We find that the commit A and commit B will be patched after commit 5 and looked as if they had never diverged. The applied B commit could contain all the change in commit 5. The other way is to run git pull to get an auto-merged commit, as what git fetch and followed by a git merge command does. Keep in mind that all these changes happen in your local repository. If you would like to introduce your change into the remote server, you will need to run git push command to push your change to the server. After running git push command, we found that the origin-dev branch pointing to the same most up-to-date commit which the local dev branch points to. You can also choose to fetch the origin first, and then do rebasing and push. This will form a series of history, but doesn't make a merged commit. Both ways can push successfully. I hope this example makes sense. The animation I made showed what happened in logic when calling these commands. You should design cases to experience it with your git command and leave yourself deep impression on the whole process, doing exercises until you mastered the concepts. It is really nice that we have the chance to talk here. By this session, we should be able to know where about the basic concepts we mentioned in the beginning in the PPT. Without exercises, you may not master it well. Although I have stressed that basic concepts is very important, I still encourage you to use git command to replay the cases we talked in the video. And it's better that you can design yourself to leave deeper impression on those basic concepts. Time limited. I haven't prepared for the git fork and the git submodule content in the video this time, but I may make some videos about that when I'm available. It is impossible to cover every details in git in the short session, but I do hope that this video can help you get rid of some very confusing concepts and help you easily to start your git journey. If you have any questions, please feel free to mail to me. Here's my contact information. You can reach me via these mails. Have a nice day.